Today in this video we discuss the probability density of complex RVs, that means random variable which is itself a complex number. Let's see. Suppose that x tilde is a complex random variable, and as usual, right? So this complex number has two components. One is real part and other one is the imaginary part. So x tilde equal to x1 plus I x2. So where x1 and x2 are both separate random variables, right? So in this case, right, I is basically a square root of -1, right? So for complex numbers, and sigma 1 square is a variance of x1, and sigma 2 square is a variance of x2, and the covariance is represented by sigma 1 2 square, which is a covariance of x1 and x2, and x1 and x2 has respective mean or expectation as mu1 and mu2. This is our assumption. I would not say assumption, these are actually predefined values of some measures, right? So now let's proceed and see how we can compute the probability density of x tilde. We'll assume that this, in this case, the x tilde is a Gaussian density function, and let's see how does it look like. So first we'll see how to compute the variance of x tilde, which is the expression you can see in the screen. It is basically expectation of x tilde minus expectation of x tilde, and which times conjugate of x tilde minus expectation of x tilde. So now let's see how to compute this x tilde minus expectation of x tilde, which is basically your right? So basically random variable minus your mean of the random variable. So putting the respective values of x tilde and expectation of x tilde, we get this expression rewritten as x1 minus mu1 plus I of x2 minus mu2, and the corresponding conjugate will be x1 minus mu1 minus I times x2 minus mu2. Right? So if a plus ib is a complex number, then its corresponding conjugate will be a minus ib. This comes from the theory of complex numbers. I hope you guys are well aware of the complex numbers. And let's see, variance of x tilde is computed as this expectation of x tilde minus expectation of x tilde and times x tilde minus expectation of x tilde, which is a conjugate. So which comes down to sigma 1 square plus sigma 2 square, and can be written as a sigma square. Basically we are writing sigma 1 square plus sigma 2 square as a sigma square. Sigma square is a separate basically summation of two individual variances. This expression, this evaluated expression comes from that, right? So this theory of complex numbers, as we deduced in the earlier in the previous screen, and this expression over there, it comes from that typical theory of complex numbers, right? If you multiply two complex numbers, suppose a plus ib and a minus ib, if you multiply these two, then it comes down to a square plus b square. This x1 minus mu1 square plus x2 minus mu2 square, this comes from that, basically from that theory. Now let's look at a different topic, or different, I would not say different topic, let's look at the typical bivariate Gaussian density. How does it look like? You can see in the screen, over the screen, it is the bivariate Gaussian density is written over there, which is f of x1 plus x2, and there's a big expression. This expression contains this x1 minus mu1 and x2 minus mu2 and a capital sigma. Capital sigma is basically the covariance matrix of this x1 in a random variable x1 and x2. So now let's put some restrictions on that bivariate Gaussian density. We'll assume that if not exactly assumption, you can say these are some conditions or restrictions if we impose on this Gaussian density. How does it look like? We'll discuss now. Restriction number 1 is if x1 and x2 are not correlated, then the determinant of the covariance matrix comes down to sigma 1 square, sigma 2 square. You know, right, basically the top right corner and the bottom left corner of the covariance matrix comes down to 0. Basically the correlation, as the correlation coefficient is 0 over there. So now the second restriction is if we assume this sigma 1 square and sigma 2 square equals to, both are equal and equals to half of sigma square. This sigma square we already saw in the previous screen that it is nothing but the sigma summation of sigma 1 square plus sigma 2 square. That is fine, but we assume but if this individual variances like sigma 1 square and sigma 2 square equals to, both actually equals to half of sigma square, then this determinant of the capital sigma or the covariance matrix comes down to 1 by 4 times sigma to the power 4. Right. So from the determinant from the matrix, from the covariance matrix, you can see the determinant is, how does it look like? We put the values, individual values of sigma 1 square and sigma 2 square, it comes down to that 1 by 4 times sigma to the power 4. Now using those expressions, putting those restrictions in the PDF of the Gaussian density, we get this expression which is 1 by pi sigma square and the exponent of minus 1 by 2 and the individual x1 minus mu1 divided by sigma 1 square plus x2 minus mu2 divided by sigma 2 square, and which can be again be rewritten as the exponent component can be rewritten as 1 by sigma square times x1 minus mu1 square plus x2 minus mu2 square whole square. Why? Because we know, right? So this sigma 1 square and sigma 2 square, summation of sigma 1 and sigma 2 square equal to sigma square. From there we can rewrite this. Now if the mean of the complex variable x tilde is mu1 plus I mu2, then this x1 minus mu1 square plus x2 minus mu2 square can be written as a x tilde minus mu tilde times conjugate of x tilde minus mu tilde. So then this PDF comes down to 1 by pi sigma square times exponential of minus 1 by sigma square times x tilde minus mu tilde times conjugate of x tilde minus mu tilde. So basically what we saw, this distribution of this complex number, so that's what we deduce from there. The Gaussian density of a complex RV is equivalent to a bivariate Gaussian density with zero correlation between random variables and the variance of each equals to the half of the sum of the variance. So that's what the conclusion is. We deduced the PDF of a complex random variable and which is equivalent to a bivariate Gaussian density with the following restrictions. We just proved it. Thank you. If you like my videos, please subscribe to my channel and do follow me.